Welcome to my YouTube channel. So today I will discuss exact differential equation, that is first order differential equation and the exact differential equation, how to solve exact differential equation, and when the differential equation is non-exact, then how to make the differential equation as exact differential equation. That is the main point in this lecture. So first take a first order differential equation dy dx. So you know this is look like this. So whenever this we take initial value problem, then we have to take y x0 equal to y0. But here I will talk about first order differential equation. Okay, so this is first order differential equation, and this equation, if this f is a function of m as a function of xy and n as a function of xy. So if this function f of xy can be written in this quotient function, then this differential equation can be written as dy dx equal to m xy n xy. Okay, therefore from this we can write m xy dx equal to n xy dy. So this is also differential equation, and from this we can also write m dx plus n dy equal to 0 is a first order differential equation where m is a function of two variables xy and n is a function of two variables xy. So this is the general form of first order differential equation in this chapter. Okay? So this equation, how to solve this type of equation? So I will discuss about that. So now let us define the total differential. So total differential, what is total differential of a function? Let us consider f is a function of two real variable x and y, and f has continuous partial derivatives of first order in D. D is a domain in the xy plane. And the total derivative of this function f denoted by df, which is defined as df equal to del f del x dx plus del f del y dy. That's you can write simply del f del x dx plus del f del y dy. So this is total differential. So what is the benefit of total differential? So if this m dx plus n dy equal to 0 from this differential equation, if you can write this as a total differential, so let us consider this is total differential df. So this becomes, so this is m we can get from this and n we can get from this, and therefore this is look like this. And if this is a total derivative, if this becomes a total derivative, therefore we can write this as d of a function equal to 0, and if we integrate both sides, then we get this is integrating df equal to integration 0, that is c. So therefore f equal to c, we get the solution. So f xy equal to c will be the solution of this differential equation, first order differential equation. So that is the benefit of total differential. So we have to find the total differential. So m dx n dy should be total differential of a function. We have to find that function. So how to find? I will discuss that. So this is the definition of total differential. So now let us define exact differential. So I have discussed total differential, and this is the exact differential. Let this expression, so the left hand side of the differential equation. So if this expression, the expression is called an exact differential in a domain D in the xy plane, if there exists a function f of two real variable xy such that the expression equals the total differential df for all x comma y belongs to D. So this expression is called exact differential if there exists a function f for which we can write this equal to df. That is, this expression is an exact differential in D if there exists a function f such that m equal to del f del x, m equal to del f del x, and n equal to del f del y. That is, we know df is total derivative if del f del x dx equal to del f del y dy. So this and the defined this expression m dx plus n dy. So this expression will be exact differential if this equal to this and this equal to this, that is n equal to del f del y. That's it. So this expression is called exact differential. So whenever this expression is exact differential, then the differential equation this will be exact differential equation. Let me repeat. If this expression is exact differential, then the differential equation, that is m dx plus n dy equal to 0, which is a differential equation, will be called exact differential equation. So this is expression, and if we write equal to 0, this becomes equation. That means this is called exact differential, and when this becomes equation, we call exact differential equation. That's it. So now I discuss one theorem from which we can conclude that when this differential equation will be exact or non-exact. This is the theorem which tells us about the exactness of this differential equation. So consider this differential equation 1, where m and n have continuous partial derivatives of order 1, that is of first order, at all points x comma y in D, and D now as a rectangular domain in this xy plane. So now D is rectangular domain in this plane. So first, if the differential equation 1 is exact in D, then del m del y equal to del m del x. So if this is exact, then we get this del m del y equal to del m del x. So where m and n are functions of x and y. Similarly, or conversely, if this equality holds, that is if del m del y equal to del n del x for all xy belongs to D, then we can say this differential equation 1 is exact in this domain. Okay. So how to remember this equality? So here with m there is dx. So whenever you partially derivative, you have to take y with m, and this is n with dy. So whenever we write del n, you have to take del x. That is opposite. So with n there is y, so y comes here and del x comes here. So if this equal, though we say the differential equation exact, and if differential equation is exact, then this equality holds. That is, the necessary and sufficient conditions for this differential equation to be exact is del m del y equal to del n del x. That means if this exact, this happens. If this happens, the differential equation becomes exact. This is the beauty of the theorem. So whenever you are given a differential equation and asked that check whether the differential equation is exact or not, you have to check that inequality. If this is not inequality, this is equality, this is relation. So if this relation holds, you have to find this and check if this quantity are equal or not. If they equal, so you can conclude that given differential equation is exact. Otherwise, if this is not equal, then this becomes not exact. So if this differential equation becomes exact, what will happen? So if this differential equation will be exact, then we can find a function f, so that we can write m dx plus n dy equal to total differential of a function, and from this we can find the solution of the differential equation. If this is not exact differential equation, then we have to multiply a constant function or a function. So what is integrating factor, IF? I will discuss in the next chapter briefly what is integrating factor, but I am giving a short hint. What is integrating factor? So you are given this differential equation m dx n dy equal to 0. So whenever I write m and n, you have to know that these are function of x and y in this whole chapter. Okay. So this is differential equation. So you have to check is this exact or not. So for that, find del m del y and del n del x. If these are equal, then this is exact, and in that case you can find a total differential for this function, and we get simply the solution of the differential equation. If this is not exact, then you have to multiply a function. So let mu is also function of xy. So you have to multiply a function, and then it becomes total differential equation. Sorry, exact differential equation. If you multiply a function with the non-exact differential equation, then this becomes exact differential equation. And in that case, this function mu is called integrating factor. That is, you are multiplying a factor with the non-exact differential equation, and then this equation becomes exact. So the main goal, whenever the differential equation is non-exact, the main goal will be what is the function, that is integrating factor. So that by multiplying this integrating factor, we can get a exact differential equation. That is challenge in this chapter. So we have to find this factor. So this is integrating factor. I will talk about this integrating factor. So let us take an example. Y square dx plus 2xy dy equal to 0. So here, if we compare this differential equation with the form m dx plus n dy equal to 0, then we get mxy equal to y square and n xy is 2xy. Okay, now we check, is this differential or this factor is total differential or not. That is, we check the differential equation is exact or not. So for that, we find del f, del m, del y, that is equal to 2y, and del n, del x, that is also 2y. So we get del m, del y equal to del n, del x. So for all x comma y in a given interval, so this will be equal. So therefore, this one will be exact differential equation. Okay. Now we have to find the exact differential of this factor. So what will be the exact differential? So for that, we have to find a function f of xy, so that we can write this equal to df. Okay. So simply, if you check this is y square and x, and here this is y. So this, if this is x into y square, then it will be if we take f equal to function of xy, that is x y square, and now if we find df, that is first y square as constant, if we differentiate with respect to x, so this will be dx, and plus let us take x as constant, and if we derivative y square, then we get 2y dy. So we get total differential. So we can find a function x y square. So from this we can write this is a d x y square equal to 0. Therefore the solution will be x y square equal to c. So this is the solution for this exact differential equation. So as these are equal, therefore this is the exact differential equation. That's why we can find a function, so that this will be total differential of a function f, and we find that f is x y square. So now see, when the equation will be non-exact, so just divide by y this equation. So therefore y dx plus 2x dy equal to 0. Now this m equal to y, that is function of xy, and n equal to 2x. Therefore if we find del m del y, this will be 1, and del n del x will be 2, but 2 not equal to 1, that means del m del y not equal to del n del x. So therefore this differential equation is not exact differential equation. So the question is how we can make this non-exact differential equation to exact. So simply we get this equation by dividing y in both sides. So now we can get from this non-exact differential equation to this exact differential equation by multiplying y with both sides. So therefore this y dx plus 2x dy equal to 0 become exact if we multiply y with both sides. 0 into y. So therefore we get this equation. So now this equation becomes exact differential equation. So we multiply a function y. So this is called integrating factor. So by multiplying a factor, if we can make a non-exact differential equation to exact differential equation, then this factor will be called integrating factor. So now we integrating this, we check this, we get this is equal. Del m del y and del n del x will be equal. So that is the integrating factor. So let us take another example. So this is given 2x sin y plus y cube e to the power x dx, x square cos y plus 3y square e to the power x dy equal to 0. So if we compare this equation with this form, dx plus n xy dy equal to 0, we will get mxy equal to this plus y cube e to the power x, and n xy will be x square cos y plus 3y square e to the power x. So whenever you are trying to check the exactness of a differential equation, you make the given differential equation in this form, and then you have to check, and after that you can compare with the theorem, and you have to check del m del y equal to del n del x is equal or not. If equal, then this differential will be exact. If not equal, not exact. So for this we find del m del y. So we get with respect to y, this will be 2x is constant, sin y will be cos y, plus if we derivative with respect to y, so this will be 3y square to the power x, and e to the power x will be constant as this is term of x, and del n del x will be, this will be 2x cos y, if derivative of x square is 2x and cos y will be constant as this is a function of y, plus 3y square will be constant as this is a function of y, and derivative of e to the power x is e to the power x. So you can simply del n del y and del n del x. So this is equal, this is equal. Therefore we get del m del y equal to del n del x. So therefore we can conclude that this given equation, given differential equation, which is what is exact, that is exact differential equation. That means we can find a function f so that it can be written as df equal to 0, and therefore f equal to c is the solution for the differential equation. So in this lecture, the main goal was what is exact differential equation and under which condition the equation become exact or non-exact. So this is the necessary and sufficient condition for a differential equation in this form to be exact. Okay? So thank you very much. If you like it, please share with your friends. And in the next chapter, I will discuss about the integrating factor. I have discussed in the previous lecture. So what is integrating factor, you know, but I will discuss it briefly in the next lecture. So for today, that's it. Share with your friends. Please subscribe my channel. I will upload the next video very soon. Tab tak keep learning and keep watching my videos. Thank you.